Imagine a future where quantum computers can tackle problems that are currently beyond the reach of even the most powerful supercomputers. These revolutionary machines hold the potential to transform fields such as cryptography, materials science, and drug discovery. However, there's a significant hurdle. Quantum computers are incredibly delicate. The quantum bits, known as qubits, that are responsible for storing and processing information are easily disturbed by even the slightest external influences. Factors like heat, light, or magnetic interference can disrupt their fragile quantum states, leading to rapid accumulation of errors. One of the most exciting avenues being explored to overcome this challenge is topological quantum computing. This innovative approach safeguards information by encoding it within the geometric characteristics of unique particles called anyons. Unlike standard particles, anyons can only exist in specific two-dimensional environments. Theoretical research indicates that they are much more resistant to noise compared to traditional qubits, making them promising candidates for constructing a robust quantum computer. Aaron Lauda, a professor specializing in mathematics, physics, and astronomy at the University of Southern California, elaborated on the appeal of a particular type of these particles. Among the leading candidates for building such a computer are Ising anyons, which are currently under intense investigation in condensed matter laboratories due to their potential realization in exotic systems like the fractional quantum Hall state and topological superconductors. The limitations of Ising anyons. Ising anyons have the ability to store quantum information through a technique known as braiding, which involves physically maneuvering them around each other. This movement alters the overall quantum state in a predictable manner, enabling the execution of quantum logic operations. However, there's a significant limitation. Braiding Ising anyons can only perform a limited set of logic operations known as Clifford gates. This means they cannot independently manage every conceivable quantum computation. To address this limitation, physicists have been investigating various strategies, such as incorporating operations that are not protected by topology, or utilizing short-range interactions between anyons. While these methods can enhance computational capabilities, they often necessitate complex error correction processes, which can detract from the inherent stability that makes anyons so appealing in the first place. A surprising discovery. Recently, a research team led by USC has made a groundbreaking discovery that could make Ising anyons universally applicable for quantum computation using only braiding. Their findings, published in Nature Communications, introduce a new particle type that fills a crucial gap in the Ising anyon framework. They have named this particle the neglecton, a term chosen because it was previously overlooked in earlier mathematical analyses. This novel particle emerges from a broader theoretical framework known as non-semi-simple topological quantum field theory, TQFT. Traditional TQFT models describe anyons using a simplified mathematical structure referred to as a semi-simple framework. In this process, any entities with a quantum trace 0 are discarded as mathematically insignificant. However, in the non-semi-simple version, these previously discarded elements remain, and one of them is the neglecton. But those discarded objects turn out to be the missing piece, Lauda remarked. It's akin to discovering treasure in what everyone else considered mathematical trash. The elegance of this new approach lies in its simplicity. Only one neglecton is required, and it doesn't even need to be in motion. The computation is entirely facilitated by braiding Ising anyons around it. Jack, addressing mathematical instability. While non-semi-simple theories offer exciting possibilities, they also present challenges. They can violate a fundamental principle known as unitarity, which ensures that quantum probabilities always sum to 1. Many researchers would view this as a critical flaw for any quantum computing model. However, Lauda's team has devised a solution. They structured their quantum encoding in such a way that the unstable mathematical behavior does not interfere with the computational aspects of the system. Think of it like designing a quantum computer in a house with some unstable rooms, Lauda explained. Instead of trying to fix every room, you ensure that all your computing occurs in the structurally sound areas, while keeping the problematic spaces off limits. In this configuration, the computational Hilbert space, the mathematical space where qubits reside, remains perfectly stable. Any issues related to unitarity are isolated in unused sections of the theory. From theory to experiment, the results of this research build upon decades of exploration into the fractional quantum Hall effect, a phenomenon observed in ultra-clean, two-dimensional electron systems subjected to strong magnetic fields. In specific scenarios, such as the nu equals 5/10 filling fraction, these systems are believed to host non-abelian anyons, including Ising types. The new fifth state has been experimentally observed and aligns with the Moore-Reed-Pfaffian wave function predicted by conformal field theory. These systems are particularly appealing for topological quantum computing due to their large quasi-particle gap, which makes it difficult for stray thermal excitations to disrupt computations. Additionally, since the anyons carry electric charge, they can be manipulated using electrostatic gates that exhibit very low error rates. The new theoretical framework enhances this by introducing the stationary neglecton as a computational anchor. If experimentalists can identify a material platform that naturally produces this type of particle, they could achieve universal quantum computing with particles that are already well understood in condensed matter physics. What's especially thrilling is that this work brings us closer to universal quantum computing using particles we already know how to create, Lauda stated. The mathematics provides a clear target. If experimentalists can find a way to realize this extra stationary enyon, it could unlock the full potential of Ising-based systems. Engineering the braids. Braiding anyons is not merely a theoretical concept, it has practical implications. In reality, it involves moving particles along meticulously designed paths so that their exchanges yield specific quantum gates. The researchers demonstrated that by braiding pairs of sigma anyons, a type within the Ising family, around groups of other anyons, controlled operations can be created that entangle qubits. They also outlined a method to minimize leakage into non-computational spaces, which is crucial because if a computation strays into unused areas of the Hilbert space, it can lead to errors. Their approach constructs these control gates iteratively, avoiding complex mathematical shortcuts like the Solovay-Kitaev theorem, parallels with Fibonacci anyons. The physical realizability of the new model may bear similarities to that of Fibonacci anyons, another powerful non-abelian type believed to exist in fractional quantum Hall systems at nu equals 12.5. Fibonacci anyons can achieve universal quantum computation solely through braiding, but their simplest chiral form cannot be realized by a straightforward two-dimensional lattice Hamiltonian. A doubled version can be, and this insight has guided researchers in developing the Levin-Wen model, a lattice framework that supports gapped, topologically ordered states. Lauda's team has been working on non-semi-simple versions of these Levin-Wen models, which continue to produce stable ground states and anyonic excitations, despite having indefinite norms in their mathematical structure. This connection suggests that neglectons might be realized in gap systems under the right conditions. Where to look next? Certain condensed matter systems, including specific spin chains with modified boundary conditions, could potentially host these new anyon types. These clues provide experimentalists with a starting point for searching for neglectons in the laboratory. Fractional quantum Hall states remain the most promising path forward, especially since researchers already possess the knowledge to create and manipulate Ising anyons in these systems. If the neglecton can be successfully realized, it would pave the way for constructing a universal topological quantum computer without relying on fragile, non-topological operations. This advancement could represent a monumental leap forward for quantum technology, offering the long-desired combination of universality, scalability, and fault tolerance. And it all began with a decision not to discard what the mathematics deemed useless.